This video is about factoring special forms and more factoring practice. Our context is that we're in an intermediate algebra course and we've already been doing various methods of factoring, and we're going to continue that with this video. Linked below in the description of this video is this file, which you're now seeing, and this is the steps for factoring polynomials outline that I've been using to discuss these topics. We're basically going to continue using the exact same outline. We've already discussed many of these methods, but of course we're extending that and covering the rest of them here with this video. And then we'll continue to use it to decide which method to use, right? It's not only knowing the methods that matters, it's knowing which one to use that matters when you're faced with various factoring problems. Our first example in our problems here listed where we want to factor, or sometimes factor completely is the instruction you might see for something like this. Our first example begins as 4x squared minus 9. Now again, we're going to refer back to our factoring steps outline, and the first step every time with any factoring problem is to try to factor out a greatest common factor other than 1 if there is one. And in this problem, you'll notice with these terms we see, there actually is not a greatest common factor other than 1. There's no common factors of 4 and 9, and only one of our terms even has a variable in it. So we skip step 1 because there's nothing to do for it. Step 2 says to consider the number of terms. Well, you can count them here algebraically. We have 1, 2 terms, and so in the category of 2 terms, we'll use any of those methods that are listed there. Now there are several, and one of them that may stand out given that this has a 4x squared, so there's a squared variable, and the fact that the coefficients of 4 and 9 are both square numbers, is that maybe this is a difference of 2 squares. That's one of our 2-term factoring methods. Now the way you need to confirm that it's that type is by trying to rewrite the problem as a difference of 2 squares. So I like to write out 2 blank parentheses, each being squared, with a subtraction sign in between them, which would be a difference of 2 squares. And if we can put something inside these parentheses that when squared would actually be the same as the original problem or equal the original problem, then it would fit this form. So you'll notice the first term being a 4x squared is such that if I put a 2x inside the first set of parentheses, then when I square that set of parentheses, I'd be squaring the 2 and the x. Of course, we would get 4x squared. So that's how we can write the first term as a square, or as something squared, you could say. The second term being 9, of course, that's really just 3 squared. So I could put a 3 in the second set of parentheses. And then, of course, this means this does fit the form of a difference of 2 squares. If there is no way to fill in these parentheses in this structure that would match this original problem, then we might have to say it's not a difference of 2 squares. So this one does actually match the difference of 2 squares form. Now you can refer to the the factoring steps outline that's linked in the description below to see that formula again, but it involves seeing it as an a squared. So the first term is like the a. In this case, it's the 2x. So it's a squared minus b squared, where the second term is the b. So for this problem, a is the 2x and b is the 3. That's assuming that the formula is written as a squared minus b squared, which is the way I have it written in that file. You could also write it with other variables represented as well, but I'm using the a and b. Now, the way that the formula works is if you know what a and b are, then the way to factor a difference of 2 squares is the same every time. It's always a plus b times a minus b. So you could write that out as 2x plus 3 times 2x minus 3. And that's it. Once you use the formula to plug in the a and b, you know that it's factored. So again, the a is the 2x, that's showing up in the front of the parentheses, and the b is the 3, so it's plus b and minus b. There's a plus 3 and minus 3. Now, it's also true, though, that The order in which you write these binomials here in the answer, the 2x plus 3 and the 2x minus 3, the order in which you write those does not matter. You could actually put the minus first. I just have the habit of putting the minus second because sometimes the difference, the minus term, the minus factor with the parentheses, sometimes that actually goes further, and so I like to put it on the end so that you can just extend it if you need to go further in some examples, though this one does not. And we know that because these two binomials that we have now are not factorable further using any of our known factoring methods. Let's try another example, which begins as 25x to the fourth minus 9y to the sixth. So again, we'll run through all of our factoring steps. The first step, as always, is to factor out a greatest common factor, if there is one. But you'll notice there is not a greatest common factor other than 1 here. So we skip on to count the number of terms. We see 2 terms. Notice then there's a difference between them. But that's not enough to know which of the 2 term methods might apply. As you can see in the list, there are a few of them, and a couple of them have a difference. So we have to go further and say, well, the coefficients of 25 and 9 are actually both square numbers. And furthermore, the exponents of these variables are both even, namely 4 and 6. So those clues all put together may make us wonder, is this a difference of 2 squares? And so we'll investigate by writing out our 2 blank terms that are squared, and in each of those blanks try to put something that when squared would give us these original terms. So notice that if I had a 5x squared inside the first set of parentheses, then squaring that would give me 25x to the fourth. That's a good sign. Secondly, we could say if I had a 3y, now think exponent rules here, I need to end up with a y to the sixth. And the exponent rules would say that whatever I have as the power of this y inside my parentheses would be multiplied with this squared, or this power of 2 on the outside. So actually that could work fine. That means if I put a y cubed inside the parentheses, then when squaring, that entire term would turn into 9y to the sixth. Okay, so again, that initial setup helps you identify what the a and the b are according to the formula. Once you know what those are, it's simply a matter of putting them in place. So I'm going to put it in the same order here as a plus b, a minus b. So that's 5x squared plus 3y cubed, there's a plus b, times a minus b, so that's a 5x squared minus 3y cubed. And so again, you can see the a and b terms within this original setup showing up in order, and that's our final factored form. Again, to ensure that it's factored completely, always go through what you have and make sure there is no other GCF that maybe you missed to take out, or at least at this point, no other no other difference of squares. And there isn't any of that here that's left, so we're done. Let's move on to some more. Our third example begins as a squared minus, and then in parentheses we have b minus 3, and then those parentheses are raised to the second power. So at first glance, this one looks different and more complicated than what we've been seeing, but let's again just go through our steps. First step is to find out if there is a greatest common factor other than 1. That's not the case here. Now you may be tempted to say, wait a minute, if I have b minus 3 in parentheses squared, should I, expand that by foiling it out or something? Well, you could try. I mean, it wouldn't be illegal algebraically to do that, but it's likely not going to make it any better. And here's why. You might also spot the fact that you actually have a difference of 2 squares already lurking in the way that this problem is set up. If I just write the first term as a, I'll have a squared. Obviously, that is the first term. If I look at the entire set of parentheses, the binomial b minus 3, then that could be seen as my second term that's squared. So really it's a b minus 3 squared, which means we still have the matching setup where a in the formula is actually a in this problem, and then b in the formula is actually the b minus 3 in this problem. So what we're seeing is the second term that is squared is actually 2 terms within these parentheses, but it still fits the pattern. So we're going to write this out as a plus b, a minus b, where that would be a plus b minus 3 times a minus b minus 3, but there's an extra kicker here, which is this b value that we have in parentheses, the binomial, it actually would have to show up within parentheses when we rewrite it here in this second step, because of this negative sign that's in front of it would have to be distributed in. So we actually have another step to take here. Let's go ahead and rewrite the first set of parentheses is fine as is, a plus b minus 3. But this second step, or this second set of parentheses, requires us to distribute that negative sign. So we really have a minus b and then a plus 3. So sometimes it's the case where students will go through this and check the answer in the back and see a plus and go, wait a minute, where'd that plus come from? Well, it's the distribution of that negative in the previous step. That can be a little tricky there, so be careful of that. All right, so we have a, that b looks bad here. That's an a minus b plus 3 as our final answer. Okay, on to our next example. This one begins as 4 minus b to the power of 2n. Now, we haven't seen much with these variables in the exponents as we're seeing in this one, but it doesn't change any of the factoring strategies or rules or methods. So let's go ahead and understand that there's no GCF here to take out of these two terms. We have two terms, which is where we consider the number of terms. And furthermore, we have a minus sign between them, which means maybe it's a difference of squares or maybe it's a difference of cubes, but we haven't even done the cubes yet. That's coming. Let's go ahead and understand though that with a coefficient of 4, it's a good hint that it could be a square, and similarly the power of the second term being 2n with an even power like that means maybe this is indeed a difference of squares. So let's try to write it out as something squared minus something squared and go back to our exponent rules that we know. So 2 squared would be 4, that's easy. And the second term, if I had b to the power of n, remember that using exponent rules, you would be multiplying the n times 2 in this scenario, which would give you 2n, which is exactly that original power. So actually that's a good fit. We have here a difference of 2 squares. I'm going to understand the first and the second items in parentheses to be like the a and the b in the formula as we've been using. So a plus b would be 2 plus b to the n, okay, and then times a minus b would be 2 minus b to the n. And again, we'll stop here and wonder, can I factor either of these binomials any further? The answer is no, there's no GCF to factor out, and so we can stop right there. Okay, let's go on to some other examples. The next one begins as 4a cubed c squared minus 16a x squared y squared. So again, back to the top of the list, look for a GCF. Now this time there actually is a greatest common factor other than one that we should be able to factor out. In fact, there is a 4 that's common with 4 and 16, and then an a would be the lowest power of the common variable, which is the a variable. But that's all we can take out. So we'll go ahead and then remain or keep going with, I like to use brackets at this level of taking out the GCF, and then put whatever would be left in them. So 4a times an a squared c squared would give us that first term, minus, and then 4a times a 4x squared y squared would give us that second term. So after simply taking out the greatest common factor of 4a, you can see we have a couple terms left. Now, early on in factoring, when we were taking out the greatest common factor, we were just done at this point. But now that we know more methods, we can look for more things to do. Notice that what's left in the brackets has 2 terms. And so, though we've already taken out the greatest common factor, maybe we can go further with those 2 terms. So let's go ahead and bring down our greatest common factor, the 4a that we already took out, but then recognize that inside the brackets, we might actually have a difference of 2 squares here, and we can do our same old test by putting the blanks. And then understanding that if I had an a times c, an ac in the first blank, then when squaring, that would give us the a squared c squared in the first term of the brackets above. That's a good sign. In the second term, we would put a 2xy inside the parentheses because when squared, that would give us the 4x squared y squared in the previous step. So indeed, this is looking like a difference of two squares inside the brackets. So to finish this off, we're going to keep our GCF out front, and then we're going to jump right to the end of this difference of two squares step, which would involve first plus second, so AC plus 2xy, and then first minus second, so AC minus 2xy following it. And that will be our final result. Again, nothing can be factored further, which is always a thing to consider when you think you're done. Let's go on to another example. This one begins as x cubed minus 6x squared minus x plus 6. So again, top of the list every time with the factoring steps. The first step is greatest common factor. You'll notice there is not a greatest common factor for all the terms in this problem. But then you'll count the number of terms and find that we have 1, 2, 3, 4 terms. Well, we know a method for factoring 4 terms already. That is factoring by grouping. So we're going to go ahead and try that method where we ideally group the first two and second two terms. Out of the first group, you could factor an x squared as the GCF of it. That would be behind an x minus 6. And then out of the second group, of course, you keep the sign in between the groups there. So I'm going to copy this minus sign straight down. But then you could factor seemingly nothing out of this second group with it just being x plus 6. But we're going to force it and factor a 1 out. We've seen this trick before. And if you force it and factor a 1 out, normally that doesn't do much for you, but it actually kind of holds the grouping method together in this case. Now remember, it's actually a negative 1, so that means inside the parentheses I'll need an x minus 6, because when I distribute that negative 1 into those, I would need to match the signs of that previous step. So we have, notice, a good thing happening here, which is that the x minus 6's in the parentheses match. We always want to see that in the grouping method, which means I'll continue with that method and factor out that matching x minus 6 to be in front, and then after it, put what was in front of those in that previous step, which is the x squared minus 1. So again, we've done the GCF stuff already, we've done factoring by grouping already, and we've just done that here in this problem. But notice that what we see in this second factor now, the x squared minus 1, actually falls into the difference of two squares method. So further, we could write this out. I'm going to recopy this as x minus 6 times, and then instead of x squared minus 1, you could think of that as x squared minus 1 squared. And really that step of writing it that way isn't totally necessary, but I'm just being super clear with that you can see it as a difference of two squares. In which case, we'll continue on here, copying down the x minus 6 in front, but then turning this into the difference of two squares factoring result, which would be an x plus 1 times an x minus 1. So we actually have 3 binomials as the result in our final answer for this one. Moving on to our next example, this one begins as 16x squared minus 40xy plus 25y squared. So again, top of the list every time. That's the best way to stay organized with these. You'll notice that there is no greatest common factor for all of these terms, at least that we could use to factor out of all 3 terms. Now, that's okay. That means you just keep going. And notice that this is, in fact, 3 terms. Now, we've done 3-term factoring already, a couple methods of it. That's in the factoring outline linked below. But this is a particular type of 3-term factoring that we haven't seen yet, and this is what's called a perfect square. Now, the good news about a perfect square is that if you forget the formula for it, you actually can still factor these types using our previously known methods for factoring 3 terms. We've done the product and sum method, guess and check is a valid method out there as well, but this method I want to use to demonstrate the perfect square method of factoring. Now, I told you the good news is that, which is that you can still use the other methods to get through this one. But if you happen to recognize the perfect square, it's actually a lot faster. Now, the bad news with perfect square is that if you forget the formula, it's really hard to use it. So I'm going to demonstrate this perfect square method here by writing out the general shell of the perfect square method, which is the blank squared, and then you match the the first sign in the problem with this formula. So it's blank squared minus, because we have a minus as the first sign between the terms here, and then it's 2 blank blank, and then plus blank squared. So there's a lot of squaring going on, a lot of blanks, but here's how this formula can work. You'd first want to spot that is it possible to turn the ends of this original problem into the ends of this formula. So in other words, can I write the first term of this formula, the first blank that's squared, as something that would equal the first term in the problem? Well, if I put a 4x inside this first blank, notice that when squaring 4x, I would get 16x squared. That's a good sign. That actually matches. But then secondly, I need to do the same thing for the end term. So again, notice if I put a 5y in that last term, then when squaring that, I would get 25y squared. That's a good sign. But there's more. You have to make sure the middle term actually matches as well, because sometimes those end terms work out as squares, as these have, but then the middle term doesn't match. So you have to make sure the middle term matches, and by doing so, you simply copy what you have put in for these end terms. So like this 5y, we just put at the end. I'm going to put here into this second blank in the middle, and then what we put in the first blank, I'm going to copy into the first blank in the middle as well. And we have to make sure that this all matches. Let me rearrange some things here. So we're putting a 4x in that first blank in the middle, coming directly from the 4x we put it in the middle, or in the first blank. Okay, so we're going to now just verify that this all actually works. The product of these factors in the middle better equal this middle term. Well, notice we have now -2 times 4 times 5. Well, that happens to be -40, so that's good. And then we have x times y, which happens to be the xy. So you have to verify, as it does in this case, that the middle term does actually match in this perfect square format. Now, the perfect square format, as you can see in the factoring steps outline, which contains the formulas in it that you'll use to memorize, the perfect square formula could work whether the first sign is a positive or a negative. So this example had a negative with that first sign, but if it were a positive, there's a version of the formula that works there as well. That sign is always what shows up in the answer. So we're going to put a open blank set of parentheses, and we're going to just square that set of parentheses, and then simply put the first sign that we had in this problem, which is the minus, right in the middle of these new parentheses we have here. And then we're simply going to take what we had in the first blank, which was the 4x, and put that in the beginning of our set of parentheses here at the end, and then take what we had at the end, that was the 5y, and put that as the second term of our parentheses. And that actually concludes the entire problem, which is why it's nice to use this formula, because you're just all of a sudden done. All you have to do is verify that the formula actually works in this middle step, and if it does, as it has in this example, you simply jump right to this end result by plugging in what you've already discovered in this previous verification step, and you're done. So again, if you had done this by factoring another way, maybe a product sum or a guess and check or some other method, you would and should end up with this exact same result. Sometimes doing it another way may result in writing out, you might get something like 4x minus 5y times 4x minus 5y, just doing it with some other method, but you'll notice that's equivalent to this answer because that's really 4x minus 5y squared. You have two of them. So writing it as squared here is the same thing, and that's how you can verify that you do have the same answer. Let's try another example. This one begins as x squared plus 16x plus 64 minus x to the fourth. So we're going to jump to the top of our factoring steps outline, as we do with every problem. And step one is check for a greatest common factor for all the terms, but there isn't one that works for all 4 terms in this case, so we skip on, count the number of terms. Now this problem has 1, 2, 3, 4 terms, as mentioned, and we have a method for handling 4 terms, but this one won't actually fit what we've already seen using that method. So that's why I wanted to put this example in here. This is what I like to call an atypical grouping problem. And yes, it's listed in our factoring steps outline. In fact, the link in that outline has a video listed with even more examples of this type on there, but this is one of them. And what I mean is this: if you try to factor the first 2 and second 2 terms like we typically try to do first, you can factor those 2 groups, but then what you get remaining won't actually match, right? We typically say, well, factor something out of the first group. You could take out an x, that'll leave you with an x plus 16. Keep the sign between them. In the second group, you could actually force this second group to be a difference of 2 squares. You could say this is really an 8 plus x squared and then an 8 minus x squared. That's using our difference of 2 squares formula that we were just using above. But notice that nothing matches in these 2 broader groups, which is usually what has to happen at this step of grouping. So we're actually not going to try to group that way, and sometimes that can be frustrating because you start the grouping and think, wait, it doesn't work. Well, that doesn't mean it's prime or not factorable. It means sometimes you need to redo the way you're grouping them. So in this example of atypical grouping, sometimes you need to group the first 3 terms together and then the last one on its own. Okay, so the reason that that fits at this point in our factoring context is because, number one, we've been doing all these methods so far. We've been using the outline. But notice that the first 3 terms here actually line up as a difference of 2 squares with what we just did in the previous example. You can go back and remember that and look at the outline, which has the formulas in it. This is a perfect square. And so we're actually going to rewrite those 3 terms as a factored form. Now, you can identify all the pieces of the square. This one will turn out to be x plus 8 in parentheses squared. Then we continue on to say, well, there's our first thing that is squared. So so far it's fitting the first term squared minus, now do we have the second term squared? Well, sure, we have x squared squared as x to the 4th there. So we actually have a difference of 2 squares lurking here since we spotted those first 3 terms as a perfect square. Which means we'll now go ahead and write out a large difference of 2 squares where the first thing, the x plus 8, shows up. So it's first plus second, first minus second. So x plus 8 plus x squared, and then x plus 8 minus x squared. So again, to color coordinate this, we have the x plus 8 showing up in its usual spot for the difference of 2 squares, and then we have the x squared showing up in its usual spot for the difference of 2 squares formula, and this is where we can finish. Now, of course, always make sure that your answer is simplified. These 2 sets of parentheses here now contain trinomials. If you really wanted to be picky, you could rearrange the order of them in descending order, so x squared plus x plus 8, and then you could say negative x squared plus x plus 8 is the second one. It really wouldn't be necessary to rearrange them, but you could. Either way, as long as you have something equivalent to this form or the step even here before it, either one of those should suffice as the finished factored answer. Okay, let's go on to another example. This one begins as z squared minus x squared plus 10xy minus 25y squared. Okay, so top of the list every time. There's no greatest common factor for all these terms. You can discover that by looking through them without too much trouble. But notice we have 4 terms, which may make you think, well, maybe grouping. Well, again, this is some more atypical grouping, and I want to point out the fact that in this one, the last 3 terms can team up as a perfect square. So if you go back up to this previous one we just did, these first 3 terms, this was the perfect square, and that was the atypical part of the grouping. Well, in this next example, that's still happening, but it's now with the last three terms. So this is a perfect square. And so we're going to utilize that to help get through this one. Now, what I mean by that is we're going to keep this as z squared from the first term, grouping 1 and 3 here. Z squared is the first term. Then we keep the sign between the groups here, so minus. And then these last three terms, when put through the perfect square formula, would turn out as x and then a minus 5y, so x minus 5y, and that's all squared. So again, this is the perfect square formula that's going from this original step into this binomial we've just written here. But the nice thing about it is that now shows that we have a difference of two squares, which is one of our formulas. So we'll go ahead and just finish by writing out that formula, which is first plus second, first minus second. So that's z plus x minus 5y, there's first plus second, times first minus, so z minus. But now again, after a minus sign, we have to put parentheses, so be careful. We have to have the x minus 5y, the second part of this, in parentheses, so that we remember to distribute the negative sign in front of them. So altogether, our final result here would be a z plus x minus 5y times a z minus x plus 5y. So there could be other equivalent ways to writing this by rearranging some of the terms inside here, as long as the signs in front of those terms match, but this is where we could stop with this one. Let's go on to another example. This one begins as 27y cubed plus 1. Now we're going to the top of the list here for our factoring methods. You'll notice there's no GCF to take out other than 1, so we can skip on and go to step 2, which is count the number of terms. You'll notice there are only two terms, and we've been dealing with a two-term method above in this video, but this doesn't fit it. This is not a difference of two squares. In fact, it's not even a difference. It's a sum. Well, if you look in our factoring outline steps, there's only one option for a sum with two terms, and it is a sum of two cubes. Now, of course, there are formulas for a sum and a difference of two cubes, and those are listed in the factoring steps outline, and they need to be memorized. They work, and I'm listing them here. The first one is a cubed plus b cubed. That's a sum of two cubes. And the result is that you can factor that automatically as a plus b in parentheses times another set of parentheses following that containing a squared minus ab plus b squared. That's the sum of cubes. The difference of cubes is very similar, and it begins as a cubed minus b cubed. So notice that initial sign there is either a plus or a minus. That's what distinguishes a sum or a difference of cubes. But then the difference of cubes turns out to be factored as a minus b as the first factor, and then following that, a squared plus ab plus b squared. So in both cases, you get a binomial times a trinomial for the result, and furthermore, all the a's and b's are even in the same spot with those. So the dangerous part is that they're so similar, it's easy to forget that the signs are different. Now there's a little trick out there that some people like. I'm going to mention it here. It's this acronym of SOAP, S-O-A-P, and the reason it can be beneficial is because it means if you look at the right sides of these sum and difference of cubes formulas, the first sign in the binomial is always the same as the original signs in the problem. So S stands for same in the word SOAP, same signs. The second sign, the second set of signs, which is the first signs in this trinomial, those are always the opposite. So O stands for opposite of the first ones you see in the binomials, which are of course the same as the original signs. So same and then opposite, and then the last signs are always positive. So that's where the AP comes in. So same, opposite, always positive, SOAP. It could be a convenient way to remember this, and double check it before you run off forgetting to change the signs appropriately here. So with our first original problem given as 27y cubed plus 1, we have to verify that this actually matches the sum of cubes, and we do so the same way we verified the difference of squares, that is by writing out just kind of a blank shell of this problem. If I can write these terms as something cubed plus something cubed, then we have a sum of cubes. So indeed, 3y when cubed would give us 27y cubed, so that works there. And then 1 cubed gives us 1, so there we have it. The a for the formula is the 3y, and the b for the formula for this cube, sum of cubes, is the 1. If we understand the formula then, which yes has to be memorized, they're written right here for us, we have then a plus b in parentheses, that would be 3y plus 1, and then close parentheses, open up a new set next to it, which contains a squared, so that would be the 3y squared. Then we would have a minus ab, so that's a 3y times 1, and then a plus b squared, which would be a 1 squared in this case. So that's the main step of just plugging in all the pieces of the formula. We have the 3y showing up in its places, and then we have the 1 showing up in its places. They each get 3 places to show up, and that fits the formula. So sometimes, as is the case in this one, you need to clean up the exponents a little bit. So I'm going to do that to rewrite this with a final answer as 3y plus 1, that's that original binomial. And then following it in the trinomial, you'd really have 9y squared, applying that squared there to the first term, and then minus 3y plus 1. So that's maybe the cleanest way to write out that answer. And then, of course, always check to make sure that what you have here remaining can't be factored further. But given what we know about factoring, that's already true here, that this can go no further. Let's try another example. This one begins as 216x minus x to the 4th. So again, top of the list is where we go on this one, and you'll notice there actually is a greatest common factor to take out of these, that is an x. So we'll factor that out and leave what else remains in brackets following. That would be a 216 minus x cubed. So after taking out the greatest common factor, we consider the number of terms that are left. We see 2 terms. Notice there's a difference of 2 terms. But as we've seen by now, that could mean a couple different possibilities. Maybe it's a difference of squares, maybe a difference of cubes. But notice with the number 216, which may or may not be, on the tip of your mind as a common square or cube number, but it actually is a cube number. So that's a hint. And then the fact that this is x cubed is another major hint that this is probably a difference of cubes. So let's go ahead and rewrite it that way. We'll keep the x out front, and then in the brackets, we're going to rewrite this as 6 cubed. Again, if the perfect cubes are not fresh in your mind, you just pull out a calculator and guess and check quickly. I think you'll find it, and you'll be more familiar with them as you practice more. So 6 cubed is 216 minus, and then of course x cubed is x cubed, which means we have part of our formula here where the a is the 6 and the b is the x, and it matches a difference of 2 cubes. And we have that formula written here above. We'll just be careful to make sure the signs are correct. We have to keep our GCF out in front for our answer so that x still has to show up. No problem, got that. But then following it, we're going to put the structure of our difference of cubes formula, where it's going to be the same sign first, so that's 6 minus x. Following it, we'll have in the trinomial portion a squared. Well, a is 6, so that's a 36. And then it's going to be the opposite sign, so plus, and then it's AB, so that would be 6 times x. We'll just put a 6x there in the middle, and then plus, and then a b squared, so that's just an x squared. And so here we have our final answer utilizing the difference of 2 squares. Maybe I'll write that down here. This is a difference of 2 squares. Okay, so there's an example of that. Let's go on to another example. This one begins as 125x to the 6th minus y to the 6th. Well, again, by now you know, go to the top of the list every time. There's no greatest common factor to take out here. Fine. We consider the number of terms, which is 2, fine. We have a difference between the two terms, okay, that narrows it down to either a difference of squares or a difference of cubes. In this case, let's go ahead and try, sometimes you're not sure if it's going to match one of those or not with a power like 6, because that's a multiple of 2 and a multiple of 3, so that actually wouldn't give it away. But the fact that the leading coefficient here is 125 does give it away. That's a perfect cube number. So let's go for a difference of cubes to see if that lines up completely here. It turns out that 5 cubed is 125, so that works. And then given our exponent rules, an x squared cubed would involve multiplying these powers together. 2 times 3 is 6, so that works fine there. So that gives us the first part of our difference of 2 cubes. The second part, using exponent rules, would work out fine as y squared. Again, we'd multiply the 2 times 3 to get the 6. Which means it matches there as well. So we have our pieces. We have our a as 5x squared, and we have our b as y squared if we're using the difference of cubes. So this is a difference of cubes formula, and we'll go ahead and just plug it all in now. So we have 5x squared minus y squared. That's the a minus b. Then we have a squared. Now, if we skip a step on that by writing, remember that's 5x squared. That's really 25x to the fourth. You're going to end up squaring that a value as we saw in the previous example. So I'm just skipping that step here, but ultimately that's a squared, and then it's going to be plus ab. Well, that's 5x squared y squared. And then plus b squared, that's y squared squared, which is really y to the fourth. And so we could stop right there. So there's our difference of 2 squareds factoring. Let's try another example. This next one begins as x to the 9th minus 1. Now, that looks fairly simple. I mean, there's no GCF, which is pretty obvious to spot because there's not much going on. So we'll skip on to the number of terms. We see 2 terms and a difference within them or between them. So we could spot that as possibly a difference of squares, maybe a difference of cubes. It's not totally obvious until you look at the power, which is a 9. The powers have to be a multiple of the formula you're trying to pick. So like if it were a difference of squares, you'd expect to find a multiple of 2 for any powers within the problem. But this is a multiple. 9 is not a multiple of 2, it's a multiple of 3. So we would say, well, maybe this is a difference of cubes. So we'll go ahead and try that form. It turns out that x cubed is x to the 9th. And this is why the power would have to be a multiple of 3 to be a cube, because you multiply those powers together. 3 times 3 is 9. That would work fine. And then, of course, 1 cubed is 1, so that's fine as well. And so we'll go ahead and use our difference of cubes formula on this one. And to do so, we'd end up with x cubed minus 1. That's the a minus b, like the first step of that. And then it's it's a squared, so that would be x cubed squared, which would actually be x to the 6th. Then plus ab, that's 1 times x cubed, which is just x cubed, plus b squared, which is just a 1. So when I say a and b, I'm referring to the formulas listed above for the difference of 2 cubes, which is exactly what we have. But notice in this example, we actually are not done. So sometimes this happens where you get the first part of the result of a difference of cubes, or even sum of cubes, being factorable further. So notice this is another difference of cubes. So this problem actually has 2 difference of cubes involved. We already did the first one, but now we have to do the next one as well. So I'm going to take this first binomial, the x cubed minus 1, and turn that into x minus 1, and then x squared plus x plus 1. That's just doing difference of cubes again. So in fact, let me use maybe a particular color to outline that. So that showed up. There's another difference of cubes, but then we have to copy down the original trinomial we had ended up with there previously. So x to the 6th plus x cubed plus 1. So ultimately, our final answer has these three different polynomial factors to it: x minus 1, then x squared plus x plus 1, then x to the 6th plus x cubed plus 1. Okay, let's do one more example. This one begins as x to the 5th minus x cubed plus 27x squared minus 27. So again, top of the list, you'll find here there's no greatest common factor for all these terms that we could take out at once. So we say, okay, fine, count the number of terms. Here we see 1, 2, 3, 4 terms. Well, we've dealt with 4 terms plenty of times already. We'll try maybe a grouping method. Now, we've also seen above here even some atypical grouping, but it may not be obvious yet if we have that or not. So let's go ahead and try the simplest grouping, which is the 2 and 2 grouping method. The first two terms here have a common factor of x cubed. So if I take out the GCF of x cubed, that will leave behind an x squared minus 1. Keep the plus sign between these groups. The second group has a GCF of 27. That will leave behind an x squared minus 1 as well. Okay, so good news is this is working out where these parentheses match, which means factoring by grouping is so far so good. We'll go ahead and then continue by factoring out that repeating set of parentheses here, the x squared minus 1, and then after it, put what was in front of those, which would be an x cubed plus 27. And then always check to see if we're done. Well, we're not. So notice the first binomial here, x squared minus 1, that is a difference of two squares. So we have to go further there. And notice that the second binomial is a sum of two cubes. So we actually have two other lurking special forms showing up in what we thought might have been our answer, but it's not. We're not done. So we're actually going to continue with the difference of two squares, this first binomial. X squared minus 1 would turn out to be x plus 1, x minus 1. We've done a lot of that by now. And then this sum of two cubes at the end here, again using the formulas above, would be x plus 3 times x squared minus 3x, and then plus 9. And so ultimately that one unfolded a couple times there. Now always check to see if you can go further, but at this point we're finally done. We have 3 binomials of 2 terms each with no GCFs involved, so those go no further. And then this last trinomial, though 3 terms is something we've dealt with so far, you could try any method. We know it's not going to work on this one. You would call that trinomial here prime, which means we're going no further. This is our final result.